would like to introduce our speakers. Dr. Donald White is professor at the School of Civil and Environmental Engineering at the Georgia Institute of Technology. He is a member of the AISC Committee on Specifications and has been a major contributor to both the AISC specification and the AASHTO LRFD bridge design specifications over the last 20 years. Dr. White has done much research on both steel buildings and bridges. In the area of bridges, he was closely involved with the curved steel bridge testing at the FHWA Turner Fairbank Highway Research Center from 1997 to 2005. He was PI and lead author of the 2012 NCHRP Report 725, Guidelines for Analytical Methods and Construction Engineering of Curved and Skewed Steel Girder Bridges. Recently, he was the PI on an FHWA-sponsored effort to modernize the AASHTO LRFD provisions pertaining to various types of non-composite box section members. Dr. White is the author of Volume 4 of the NSBA Steel Bridge Design Handbook and has co-authored AISC design guides on the topics of stability design and design of web-tapered members. He has received many awards, including the 2009 T.R. Higgins Lectureship Award and a 2018 Lifetime Achievement Award from AISC. Dennis Golovec is a senior technical principal with WSP, and his current assignment is working with the Florida Department of Transportation Structures Design Office in Tallahassee. He's been in the bridge profession for over 30 years. His experience includes the analysis, design, and review of steel and concrete bridges with an emphasis in the analysis and design of horizontally curved steel girder bridges. He is a member of the Transportation Research Board, AKB 20 Steel Bridges Committee, and AASHTO NSBA Steel Bridge Collaboration, and a former member of AASHTO CBS Technical Committees T5, T12, T14, and T17. He has been involved in numerous research projects involving specialized skills in finite element analysis and innovative material usage. He received his bachelor's and master's in structural engineering from the University of South Florida. He occasionally teaches graduate classes at the Florida A&M, Florida State University College of Engineering. Dr. White will be our first speaker today. So Don, thanks for being here. I'm not seeing your, okay, there. I see your screen, so I'll let you take it from here.
Okay. Thank you, Nate. Can everyone hear me okay?
We can hear you.
Okay, great. All right, well, hello to everyone connecting in today. I'm pleased to be speaking to you from the center of the political universe here in Atlanta, Georgia, at least for the next 2 months. I'd like to give you an overview of the results from our recent Florida DOT-supported research on the behavior and line girder analysis of skewed straight steel I-Girder bridges. Get it to advance. Okay. So the research on this project was a collaborative effort of myself, my doctoral student Ajit Kamath at Georgia Tech, along with John Heath, Brian Adams, and Raj Anand at Heath and Lineback Engineers. Vicki Young was the project manager for this effort, and the project received excellent input and guidance from our Florida DOT Steering Committee, and that was composed of Christina Freeman, Ben Goldsberry, and Dennis Golovec, who you'll hear from second here in this presentation. The key focus of the research was basically to evaluate the extent to which simple line girder analysis methods can be applied for the design of straight steel I-Girder bridges having small to moderate skew. I'd like to first give you a broad overview of behavioral attributes of straight skewed steel I-Girder bridges to set the stage for the discussion of this research problem. I'll then walk you through what we've accomplished on the project, and Dennis will then present a fairly comprehensive example illustrating the application of the recommendations. I'll then come in and just wrap up with a few brief professorial remarks. So let's get to it. The simple graphics you see at the top of the slide here show the deformations that occur when vertical loads are applied to a group of I-girders, a couple of I-girders here, tied together by end cross frames at skewed bearing lines, as well as intermediate cross frames within the span. So you can see a top view looking down on the bridge and kind of how the bridge is, this two-girder system is deforming. A kind of an elevation view from over on one corner, and then an isometric view on the left. Basically here, the end cross frames induce a twist in the girders due to compatibility of deformations. The girders can't really rotate about their major axis at the bridge abutments while staying connected to the end cross frames without twisting to accommodate the rigidity of the bearing line cross frames or diaphragms. Basically, the bearing line cross frames or diaphragms are going to want to rotate and there's essentially a rigid diaphragm in effect within their plane. They rotate about the bearing line. In addition, the intermediate cross frames and the girders induces twisting due to the different girder vertical deflections at the points where the cross frames connect to the girders. In addition, when we consider the behavior of the overall bridge three-dimensional system, particularly of straight I-girder bridges having parallel skew, the shortest span between the supports is along the shortest plan diagonal. You see here by these arrows. The bridge deck and the cross frames along this diagonal tend to attract greater forces since this is the relatively stiff load path in the system. NCHRP Project 725 and 2007-355 show that these effects can be mitigated by using discontinuous cross frame layouts having sufficient offsets and or staggers. Several variables often used as indices to quantify these effects are the skew index, I sub s here, which is basically the length between the fascia girder bearings along the span, divided by the overall span length, and the skew angle, theta, which is defined as 0 when there's no skew. Now, theta can range up to values as high as about 50 degrees or so for what we're going to define as moderate skew in this talk. In addition, NCHRP 725 found that when the skew index is less than about 0.3, line girder analysis is able to calculate non-composite dead load bending moments and vertical deflections with a worst case normalized error less than or equal to 12%, meaning the torsion and the load path attributes of the behavior I showed you in the previous two slides tend to be a relatively minor consideration in those cases. However, the skew angle itself, theta, is also important, particularly in terms of local behavior near the bearing lines. The motivation for the new research we conducted for Florida DOT was that recognizing the potential need to capture the three-dimensional behavior effects in the structural analysis for design, the Florida DOT Structures Design Guidelines currently require a refined method of analysis. That could be a 2D grid. You'd want to satisfy the NCHRP 725 requirements for that, or 3D FEA if the bridge has a skew index between 0.2 and 0.6. And 3D FEA would be required if the skew index is larger than 0.6. This implies that line girder analysis would be only sufficient for a skew index less than or equal to 0.2. Now, between the years of 2000 and 2014, Florida DOT built approximately 250 steel I-girder bridges with the skew index less than or equal to 0.3. The NCHRP findings from Project 725 suggest line girder analysis potentially can be applicable for bridges having a skew index up to this amount. The use of discontinuous cross-frame layouts with sufficient offsets and or staggers also can potentially extend the line girder analysis even further. With all that in mind, the objective of this project was to understand more fully the behavior of steel I-Girder bridges with skew indices up to and slightly larger than 0.3. We wanted to determine when line girder analysis can be used in lieu of a refined analysis for these types of bridges. And the objective was to develop recommendations for how to apply the line girder analysis. So that involved both direct estimation of girder major axis bending moments, vertical shears, bearing reactions, vertical displacements, with adjustment wherever adjustments might be needed. What we might call semi-direct estimation, which would include estimating girder layovers, and what I'll call indirect estimation, where we need girder flange lateral bending stresses and cross-frame forces for design. Now, the approach taken in this research focused on the design and execution of a comparative parametric study between the results of refined 3D FEA design analysis models and line girder analysis models. These studies focused on 20 existing straight skewed bridges selected from the Florida DOT inventory, plus another 6 set of redesigns of 6 of these structures using a discontinuous cross-frame layout with recommended offsets and or staggers. And so that gives a total of 26 bridges that were studied here. Now, the characteristics of these bridges included skew indices from 0.15 to 0.47. So what we might refer to as small to moderate skew indices, bearing line skew angles ranging from 10 to 58.7 degrees. 21 of the bridges had parallel skew and 5 had non-parallel skew, so 21 plus 5 adding up to 26. There were 16 of these bridges that were continuous span, 10 were simple span. For the cross-frame layout, 16 of the bridges had contiguous cross-frame layouts, 8 had discontinuous cross-frame layouts, and 2 of the bridges had contiguous cross-frame layouts that were where the cross-frames were parallel to the skew. All the bridges in the study had steel dead load fit detailing of their cross-frames, which is the usual Florida DOT practice. And for all of the bridges, basically we did a complete range of calculation of dead and live load responses, including we studied stage deck placement for 4 of the 26 bridges. For these studies, we used the CSI Bridge software version 21.0.2 for the 3D FEA as the benchmark or the gold standard, if you wish. We verified that against Midas Civil for 2 bridges. And we used LRFD Simon version 10.3.0.0 as the platform for the line girder analysis. To give you a quick feel for the different bridges studied, I'd like to flash through a few slides showing a few plan sketches. Bridges 1 and 2 that you see here had some of the largest combined skew angles and skew indices of the bridges studied. They represent the same bridge with a contiguous cross-frame layout on the left and redesigned with a discontinuous layout on the right. Note that the labels underneath the bridge plans here show the span length, LS, the width between the fascia girders, WG, the skew angle of the bearing lines, theta, the skew index, IS, and the ratio of the minimum offset of the cross frames relative to the bearing lines or to the other cross frames, that divided by the girder flange width. So OMIN divided by BF. All these are variables that we can use to help characterize the bridge behavior. Note that in this particular case, the discontinuous layout on the right uses 36 fewer cross frames than the contiguous layout on the left, which and that can, of course, provide substantial cost savings. Bridges 5 and 6, that you see here, utilize contiguous cross-frame layouts similar to Bridge 1, but with smaller minimum offsets. Bridge 6 being a 2-span continuous structure. Here's another 2-span continuous bridge we studied, but in this case with lots of contiguous cross frame lines frame directly into the bearing locations, which tends to exacerbate what often many of us refer to as nuisance transverse stiffness effects, giving high local cross-frame forces. Bridge 4 relieves this problem situation by providing recommended ample offsets, taking out 49 selected cross frames to break up the flow of the transverse forces and soften up the system transversely, and using a local lean-on cross-frame detail at the obtuse corners actually the acute corners of the plan. Bridge 8 is another example where the intermediate cross frames are offset relative to one another, but at a relatively small spacing such that they tend to induce some fairly large flange lateral bending in the girders, while acting nearly as if they were contiguous lines. And bridges 9 and 10 here show additional contiguous and discontinuous cross-frame layouts. Note that bridges 8 and 9 also don't have cross frames along the intermediate pier bearing line, but frame intermediate cross frames into the pier bearings instead, while bridge 10 has a recommended continuous cross frame line at the in intermediate pier. We recommend that that's really the better detail. What we found, that's the better way to frame these generally, combined with ample offsets of the intermediate cross frames relative to the pier. Optimal layout of cross frames is not the main subject of the webinar here, though, so I'm going to get off that soapbox. And in fact, the focus of this project was to capture responses for a relatively complete range of possible layouts. So I'd like to rapidly click through a few more bridge plans, and then let's get down to business with the main topic of the webinar. The bridges 11 and 12 you see here are 3-span continuous designs we considered. Bridges 13 to 16 are different 4-span continuous bridges, with bridges 13 and 14 being relatively narrow relative to the span lengths. Bridges 19 and 20 here are simple span designs with unequal spacing of the girders and splay of several of the girder lines, framed with contiguous and discontinuous cross-frame lines. Bridges 21 and 26, here's examples of bridges with a small skew angle less than 20 degrees. So AASHTO allows us to frame the cross frames, in this case, parallel to the skewed bearing lines. Bridge 26 is a 2-span continuous design, represented by the little bit longer line that you see there in the middle of the plan view. Bridges 17 and 18 are additional designs with contiguous and discontinuous cross-frame layouts with relatively small offsets at a number of locations. Bridge 22 is a 2-span continuous bridge with a contiguous cross-frame layout and ample offsets at most, but not all locations. And lastly, bridges 23 and 24 here are different 2-span continuous designs with ample offsets at some, but on not all locations. And in particular, bridge 23 would tend to have some major stiffness in the transverse directions around its intermediate pier location due to the use of both a contiguous line of cross frames along the intermediate pier line, as well as intermediate cross frames framed directly into the pier bearings. All right, so let's get down to business. This slide lists the key responses for the bridges studied in this research, ranging from what I would call direct and semi-direct calculations in using LGA in items 1 through 7 here. We looked at calculation of the underlying live load distribution factors, both approximate equations as well as exact live load distribution factors from 3D FEA as item 8, and the girder flange lateral bending stresses and cross frame and diaphragm forces, which can't be determined directly from a line girder analysis in 9 and 10. The project deliberations involved a number of key modeling decisions. First, in the 3D FEA, using CSI Bridge, we set up our models such that the bearing lateral constraint effects were effectively negligible. Basically, stay away from that. You want to design your bearings so that you're not inducing some significant lateral constraint that you might have that you really don't want to have at your bearings, in terms of locking things up in the bridge. We used a stiffness reduction factor of 0.65. That's basically following AASHTO current recommendations for single angle cross-frame members, flange connected T's and channels. That accounts for connection eccentricity effects in reducing the axial stiffness of those cross-frame members. In terms of the line girder analysis in LRFD Simon, of course, this line girder analysis would be limited to bridges that satisfy AASHTO LRFD Article 4.6.2, its requirements for line girder analysis. The concrete dead load, composite dead load, including barrier rail and future wearing surface load, and cross-frame miscellaneous steel weights were distributed equally or uniformly to all the girders. That's a fairly common practice that many engineers use, and it's discussed in the NHI course guidance, the 2010 NHI guidance course on curved and skewed steel arc girder bridge design. The AASHTO live load distribution factors were employed, with the exception that the Article 46222E reduction in the moment live load distribution factor for skew effects was not used in this work. We did use the AASHTO skew correction factors for shear, though, obtained from these particular AASHTO tables that you see here, and we applied those to the live load distribution factors from the AASHTO tables, as well as to the results from rigid cross-section analysis. And lastly, in the case where we were looking at the girders with the bridges with the splayed girders, we used the girder spacing at 2/3 of the span length into the span in the calculations of the live load distribution factors. In addition to the quantities shown on this slide were used to measure the differences between line girder analysis and 3D FEA results. And our goal was to determine the bridge limits within which line girder analysis could estimate the responses within the tolerances that you see in the third column here. The primary measure that we used in the majority of the things that we're looking at is the professional factor, rho max, which is basically the ratio of the calculated 3D FEA result to the calculated line girder analysis result. Professional factor borrows terminology from the structural reliability area, but really all you want to think about here is, oh, okay, if I got a rho max and it's greater than 1, my 3D FEA is telling me that this response is larger than what I predicted from line girder analysis. If it's less than 1, the line girder analysis is conservative compared to the 3D FEA. For measuring the differences between the vertical displacements, we found that alternate measures that are shown here as epsilon max 2 and 3 were more lenient and more appropriate. Epsilon max 2 is the difference between the line girder analysis and 3D FEA vertical displacements divided by the span length. And epsilon max 3 is basically the maximum difference of the differences between the predicted vertical deflections for the innermost girder within the span, labeled G3, and the fascia girders that are labeled G1 and G4. Both of these difference measures are similar to measures that are commonly used for quantifying final deck smoothness, although we really aren't implying a direct relationship between girder displacements and deck smoothness here. The selected tolerances here are 0.0005 and 0.001, or 1 in 1,000, 1 in 2,000, are representative of separate tolerance values that would be employed typically for considering deck smoothness. So let's look at some findings and recommendations together. First, for discussion and application of the findings, we found that it was useful to subdivide the bridges into 3 categories, 1, 2, and 3, listed at the top of this slide. The first category corresponds to parallel skewed bridges. And any of these have to satisfy the AASHTO Article 4.6.2. But this first category has skew angles less than or equal to 20 and a skew index generally less than or equal to 0.15, intermediate cross frames oriented parallel to the skew. The second category are basically parallel skewed bridges having theta less than or equal to 50 everywhere. In this case, if theta is greater than 20, the cross frames would be required to be perpendicular to the girders by AASHTO. And this category has skew index less than or equal to 0.3. And then category 3 is where we try to eke out a little bit more with applicability of line girder analysis. Theta up to 50 degrees and skew indices between 0.3 and 0.4, or having skew angles less than or equal to 30 and skew index between 0.4 and 0.45. Now, to cut to the chase, one finding of the project was that line girder analysis is not recommended for parallel skew bridges that don't satisfy these above restrictions in categories 1 through 3. Also, we're not recommending, based on our work, use of line girder analysis for non-parallel skew bridges. That's where the deviation between the adjacent support lines is larger than 10 degrees. Anything less than that will allow it as being considered parallel. If you've got splay of the girders larger than 3 degrees, or if you've got a change in the deck width within a span larger than 15%, we recommend not trying to push toward line girder analysis with that sort of a bridge. And if you have girders with extreme depth to width ratios larger than 5, it's probably not a good idea. You get some sensitivities in terms of girder flange lateral bending once you're getting into bridges like that. So basically, there are significant difficulties in meeting the selected tolerances I showed you on the previous slide when we don't meet the category 1 through 3 requirements, or if we're getting into some of these other areas listed here at the bottom of the slide. Now, regarding the girder moments and vertical shears, we found that we were, through all the studies we have here with the category 1 and 2 bridges, our Romax values were less than or equal to 1.02 in all cases for positive and negative bending moment. Our Romax values were less than or equal to 1.05 for girder shears in all our cases. Now, part of the reason for that is because of the conservatism that we get brought into the picture from the AASHTO live load distribution factor equations. In addition, kind of pushing out a little bit further into the category 3 bridges, they're in particular, one of the category 3 bridges, bridge 6 that I'll show you here in a second, it had a Romax of 1.06 for positive bending, 0.96 for negative bending moment, and 1.16 for shear in the fascia girders. And here's kind of a result looking at different bridges. And this particular bridge 6 is where you see a black diamond that's kind of the highest black diamond here in the plot, plotting Romax versus skew index. This is a Romax for shear here in this case. You can see a lot of bridges are performing pretty well, but we might have a little bit of conservatism. The X's are where we have these bridges that violate the categories 1 through 3. And you can see, particularly once we get to higher skew indices, we're kind of getting up to Romax values that would be a lot higher than what we'd like to see. And the bridge 6 plan view is what you see here. But essentially what was happening here for this bridge was we were getting into a case where contiguous cross-frame lines, a very wide bridge, and some of the contiguous cross-frame lines coming in with not so big of an offset relative to the next points, that basically creates a stiff path in the system that tends to be a little bit problematic with causing three-dimensional response and making it harder to predict things with the line girder analysis. Typically, we found that the fascia girders have larger Romax in our at least in the bridges we studied for moment and shear compared to the interior girders in the spans. Our girder Romax values are smaller in bridges having discontinuous cross-frame arrangements with recommended offsets and staggers. So you gain some benefit there with the line girder analysis being more applicable when you have good layouts with offsets and staggers and discontinuous cross-frame arrangements. We're seeing clear spikes in Romax values for the strength 1 vertical shear forces in the fascia girders for the bridges studied that fall outside of the categories 1 through 3. Regarding the girder bearing reactions, we found that we needed to juice the reactions a bit at the obtuse corners, at the abutments, and at the piers in continuous span bridges by a factor of 1.10 for the bridges in design categories 2 and 3. This is in addition to the application of the AASHTO LRFD Article 46223C live load skew correction factor to the reactions. The plot here shows a representative result for reactions versus skew index prior to the multiplication by 1.10. You can see here that we're basically trending a little greater than 1.0 for a significant number of the bridges we studied. And so if we hit the calculated demands for the reactions with a 1.10, then that brings these rho factors down so that we're not kind of pushing the edge of the envelope there so much. Regarding the total dead load vertical displacements, which are important for determining the vertical cambers, what we found was that this is often the most challenging target for accuracy of the line girder analysis. This is basically because the total dead load displacements don't really have the benefit of offsetting live load estimates, which is the case with the previous results that I was just showing you. Say, if we're looking at strength 1 estimates and the conservatism of the live load distribution factor kind of helps us out to make sure that we're not getting any significant unconservative results. Also, conservative displacement element estimates, if we're talking about estimating displacements and calculating girder cambers, that can be just as problematic as unconservative displacement estimates. So that kind of makes this area more difficult. What we found here is that the bridges that fall outside of categories 1, 2, and 3 are having more difficulty in being able to satisfy the recommended tolerances I showed you for the vertical displacements, but that for the bridges in these 3 categories, the line girder predictions of the total dead load, steel dead load fit displacements meet or only slightly exceed the target requirements. The plots on this slide show the difference measures epsilon max 2 on the left and epsilon max 3 on the right, the absolute value of them, for the total dead load displacements, along with the tolerances of 0.005 and 0.001 marked by the bolder horizontal line. And then we're plotting that versus skew index here. You can see that there's a lot of scatter in the results. Since if you really want to be honest about it, there's a heck of a lot more going on here than can be quantified by just the skew index. However, the general trend is clear. The bridges that would be permitted for line girder analysis under categories 1, 2, and 3, which are listed as your LGA and minimal bridges here and shown by the black diamonds. You can see that we're either tending to be below the tolerance or going only slightly above the tolerance for those bridges. Determining the layovers at the bearings under the total dead load is a fairly important consideration for skewed steel I-Girder bridges. The project evaluated a simplified compatibility of deformations estimate for the layover. The estimate is based on the assumption of steel dead load fit detailing of the cross frames. So basically what this means then is that the girders are already approximately plumb under the steel dead load. So therefore, the girder layovers under the total dead load are tied entirely to the concrete dead load deflections. The layover estimate starts with an estimation of the girder major axis bending end rotations under the concrete dead load at the bearings. We're getting that by dividing the deflection at 1/10 of the span length by the span, the 1/10 of the span length, okay? Given this particular rotation, call it alpha, and given the bearing line skew angle theta, the girder twist can be estimated by simplified compatibility of deformation analysis as phi is simply equal to alpha times tangent theta. And then lastly, we can multiply by the web depth to estimate the layover, that is the transverse deflection at the bearing line at the top flange of the girders. Lastly, in terms of responses that can be determined directly from LGA, AASHTO Article 25262 specifies a distribution factor that's multiple presence factor M times number of lanes in L divided by number of girders in G, as you see at the top of the left-hand plot here, for calculation of the girder live load vertical displacements from line girder analysis. It's basically based on an idealization of equal girder stiffness and equal girder deflections within the bridge. However, some significant three-dimensional actions occur in skewed bridges, even for small to moderate skew, that don't line up with this assumption very well, so leading to a significant underestimate of the girder live load deflections. So that's what you're seeing here on the left-hand plot. The rho value is greater than 1, meaning underestimate from the line of the 3D FEA results from the line girder analysis. We found, though, that the AASHTO live load distribution factor for moment works reasonably well, kind of an accurate to conservative way to use that to estimate your live load displacements. And the results for that for the bridges we studied are shown here on the in the plot on the right. Now let's discuss the calculation responses that can't be obtained in any direct way from the line girder analysis. Regarding the girder flange lateral bending stresses, we've recommended an improvement of the rules in the commentary to AASHTO Article C 6.10.1. Okay, that'd be the commentary to Article 6.10.1. Regarding the cross-frame forces, we've recommended a table of coefficients that I'd like to show you. And these estimated forces that we can get from this table of coefficients, they're to be added to other calculated cross-frame forces due to wind load or eccentric loads on overhangs during construction, etc., to obtain the required forces for the cross-frame design. Basically, the table of coefficients gives you an estimate of the cross-frame forces that are coming from the aspect of the applied loads on the bridge and what you're getting from the skew effects within the structure. Stability bracing considerations are already considered in the coefficients I'm going to show you in the table of coefficients. In other words, there's no need to calculate separate stability bracing cross-frame forces. And in addition, generally speaking, AASHTO requires that you satisfy restrictions on L over R min in your cross-frame member designs. For straight skewed bridge cross-frame members, generally it's recommended that you should not be considering those as primary members. For straight skewed bridge, your cross-frame members should be considered as secondary. My preference is to lean toward using L over R min of 120, though, just to add a little more belt and suspenders there for those cross-frame members. This slide shows a table of FL values the designer can use to estimate girder flange lateral bending stresses at different locations in category 1, 2, or 3 bridges with continuous or discontinuous cross-frame layouts. The estimates depend on the girder. Is it exterior or interior girder? The location within the span, and the minimum offset with respect to the girder flange width. So as a designer, you basically step through this table and determine the flange lateral bending estimates at different locations within a given bridge. This is a little more elaborate than the current AASHTO approach in Article C610.1, but it's actually easier to apply this tabular form than the current AASHTO rules, which are provided just in a long paragraph description there in the AASHTO commentary. In addition, the current AASHTO Article C610.1 requires a fairly involved consideration of the relative girder dead and live load major axis bending at the different cross-frame locations, bending moments, to determine an apportionment of the unfactored FL values to the different load cases, since the basic FL values are just nominal FL. So how much is that dead, how much is live, etc. Doing that ratioing of moments and then trying to apportion things, in our view, is far too involved given the coarse nature of these predictions that we're already starting with. And so our recommendation is to use the weighted average values that you see here on this screen, 1.6 for strength 1, and you can 1.2 for service 2, you can see here, 1.75 for fatigue 1, 0.8 for fatigue 2, although we're still mulling over those values a bit. Some of the values in those nominal factors would include dead load, and so can we pull down factors here for fatigue 1 and fatigue 2 a little bit? We're still looking at that a little. This slide here shows the table of coefficients for calculation of the cross-frame forces. The load effect column and the next to last column of the table, focusing on the coefficients for strength 1 and strength 2, are highlighted in yellow to draw your attention to those columns. So basically, to use this table, you start with the cross-frame case that you have. So for intermediate cross-frames, either intermediate cross-frames using offsets and staggers greater than or equal to 4BF throughout the span, or contiguous intermediate cross-frames or intermediate cross-frames where your offsets and staggers are less than 4BF. So then you pull your coefficient there from what the column, if it's strength 1 or service 2 that I have highlighted over there on the far right, for each of the load effects. Basically a shear force, a top flange cord connection level force, and a connection level force on the bottom flange. Then you do the same thing for the cross frames in the bearing lines, depending on the characteristics of your cross frame framing that you have in the bridge. Then once you've got these force effects that are percentages of your girder shears or your girder moments, you then work with those in the worst case direction with the cord level forces or the shear force to get an estimate of your cross frame member forces for design of your cross frames. Dennis will show a little bit more about this shortly. So I want to wrap up and then hand off to Dennis. So just give you a summary here. For category 1 bridges, everything that we're doing here, if it's LGA, we need to satisfy AASHTO Article 462. Category 1, we're talking about theta less than or equal to 20 and a skew index less than or equal to 0.15, cross frames parallel to the bearing lines. And so all the rest of the bullets here basically tell you what you can do. You get your girder design demands, your cambers directly from your line girder analysis, done. No other adjustment. Calculate your bearing reactions from line girder analysis. No other adjustment. Just get it from your line girder analysis. Calculate your girder in layovers under total dead load using the simplified compatibility of deformations analysis, the equations from that I showed you earlier. Neglect your effects of skew on your flange lateral bending stresses. Kind of flew past that in the table, but the table with the flange lateral bending stresses basically said, oh, in this case, use flange lateral bending stress of 0. You determine your cross-frame forces due to the skew effects using the table of coefficients I showed you. You determine the live load deflections using live load distribution factor for moment. Now, what I'm going to show you next for categories 1 and 2 is exactly the same as this, except for what I have highlighted in bright blue. So here, again, when we look at these bridges, there's larger limits on skew index and skew angle. The only differences with what I just explained for category 1 is we need to juice the bearing reactions by 1.1 at the obtuse corners at the abutments, simple or continuous span bridges, and the fascia girders at the piers in a continuous span bridge, in addition to applying the skew correction factors. And when we get the girder flange lateral bending stresses due to skew effects, we've got improvements upon the AASHTO LRFD Article C610.1 recommendations that I showed you as a tabular form. And here's a couple of bridges that would apply here, bridge 3 and 4 that I showed you earlier that match this particular category. All right, so we've reached the point where I'm going to hand this off to Dennis. He's going to walk you through a really good design example. Dennis.
Thank you, Don. Just want to share the screen. Nate or Don, can you tell me that the screen is now showing on my outline slide?
Yep, that's what we see here, Dennis.
All right, thank you. And thank you for joining this webinar. As Don mentioned, I'm going to look at a design example. Is the main purpose of this part of the presentation. But first, I want to go back and look at some of the common loading combinations for straight steel I-Girder bridges, review the approximate methods of analysis of the BDS, and then just go back over these recommendations that Don has just talked about in the applicability, the live load analysis, and using Simon, and then we'll get into the design example. So first off, the common loading combinations for steel bridges is strength 1, which is the member strength. Service 2 is our permanent deformation. Then we have our fatigue loading combinations, which are our stress ranges. And then service 1, which is the optional live load deflection criteria. And on the right here, you can see all those load factors associated with those combinations. A very important loading combination is constructability, but I am not going to cover that in this presentation. All of these combinations have its distinct HL93 loading patterns, so I just wanted to review that. In strength 1 and service 2, we have our design truck or our tandem in combination with our lane loading. We usually loaded up the bridge with as many lanes as possible, and we also have the multiple presence factor on that. For service 1, which is the optional live load deflection, we either use the design truck alone or the 25% of the design truck plus the lane load. And as Don mentioned, this is all the live load distribution factor would be based on equal distribution. And the multiple presence factor is also applied. However, when we get to fatigue, it's now the single truck with 6 axles and only in 1 lane. And if you use the equations in the table, you actually divide out by 1.2, the multiple presence factor, if you're not using the level rule. So let's review the approximate methods of analysis. A steel girder with concrete deck is identified as a typical cross-section A. And these articles state that if you want to use the table values, as Don mentioned, your deck has to be constant. The number of beams should not be less than 4, but they do allow 3 beams for type A. But this study only looked at 4 or more beams. Beams need to be parallel and have the approximate same stiffness. The DE, which is the center line of web to the curb, has to be less than 5.5. And of course, you have to meet one of these cross-section types, which we are type A. It further states that if your beam spacing exceeds the range of applicability, you use the level rule. And if the bridges does not meet this article, you should really use 463, which is the refined analysis. Also in this article, it states that if you meet these conditions, your permanent load, your concrete deck, may be distributed uniformly among the beams. So the next 2 slides talk about the live load distribution factors. The first slide is about moments. The second slide is about shears. And each slide has it broken up between interior beams and exterior beams. And we know we have to check for the 1-lane or 2-lane conditions, and you see the range of applicability here in this chart to the right. And I also circled the kg factor, which is the longitudinal stiffness parameter, which I'm going to talk about later. For exterior beams, you now have the level rule. For 1 lane, you still have the 2-lane, but they have the added check of the rigid cross-section analysis. And we have to keep in mind that for strength 1 and service 2, we're going to use the greatest G. Fatigue, we always use the 1 lane. And for moments, if we use this formula, we have to divide by 1.2. But for shear, we're going to use 1.0 since we're going to either use the level rule or the rigid cross-section analysis. And as Don mentioned, we're not taking into account the moment reduction factor allowed by the code. Shear, I show the formulas here. Same thing, 1 or 2 lanes. Again, for the exterior girder, the 1 lane is by the level rule, or you have to check for the 2 or more lanes. And then again, you have the additional check of the rigid cross-section analysis, and you must use the appropriate multiple lane reduction factor for the load case you're looking at. Now, in addition to those load distribution factors for shear, there's the skew correction factor, which needs to be applied for any time you have a line of support that is skewed. And as we mentioned before, this was applied to both the level rule and the rigid cross-section analysis. And if this bridge unit is connected and behaves as a unit, usually by cross frames, you only have to apply this skew correction factor for the exterior or first interior beams, as I show here. And basically at the obtuse corner, it would be the full factor, which is going to be greater than 1. And then you can linearly decrease it to 1.0 at the midspan. But Simon does not do that, and neither did we in the study. So we use that factor all throughout the length of the girder. This chart shows the formula for the skew correction factor. As you can see, it also has the kg factor in it. It also has its own range of applicability. I also want to mention about the effective flange width. You know, for most cases, you can take the tributary width perpendicular to the axis of the member, and it also has a maximum skew angle of 75 degrees. So I just want to mention a little thing about the longitudinal stiffness parameter. Up here in the upper left is the formula for it. And the commentary of the code recognizes that most steel girders, I-plate girders, are not going to be prismatic. And so you can base the kg on average properties. And also in the formula for those distribution factors, the value of L changes between checking for positive and negative moment. And so you actually will have a distribution factor for positive different than the negative moment. But what's done in Simon is they use what I call is a weighted average of averages. So kg is computed at 20th points along each span. And the correct L is used in those kg formulas when they're looking at positive and negative moment areas. Then they take the average kg for that span, and then they use a weighted average of all the spans to compute a final kg factor So we're only going to get one distribution factor for the entire length of girder. The skew correction factor is done similarly, but instead of taking a weighted average, it just uses the largest value for the shear distribution factor. The code also allows you to use a simplification for the parameters that use kg, and here I show that 1.02 is used for moments and 0.97 is used for the skew correction factor. And of course, that's based on the owner's concurrence to use these values. And we'll take a comparison of that later on. Finally, just to go through the research recommendations again as we get into the design example, the applicability, you must meet the 4.6.2 requirements. However, as Don mentioned, if the deck width or the girders are slightly splayed up to 3% or 15% in deck width, we're going to say that's good enough as being constant width. The girders, again, have to be parallel. The supports have to be parallel, but if they vary from each other less than 10%, then we're going to call them parallel supports. The D over BF has to be less than 5. That is a little more restricted than the code, which is less than 6. And of course, you have to fit in these categories 1, 2, or 3, which I repeat here on the right side. So after you meet those requirements, your live load analysis is going to be based on the live load distribution factors of the code. You're also going to use the skew correction factor, which also needs to be applied to the level rule or the rigid cross-section analysis. For cases 2 or 3, the strength 1 vertical reactions need to be increased by 10% when you're looking at the obtuse corners, either at the end bends or piers. Since you met all these conditions, you can then take your dead loads and distribute them equally to all girders. And as Don mentioned, they use the LRFD Simon program for the line girder analysis. And you must recognize that that program does not check the rigid cross-section analysis, and you have to do that outside of the program. So let's get into the design example, which is a 3-span continuous bridge. Span 1 and 3 are 140 feet. Span 2 is 180 feet. It has an out-to-out width of 54.8 inches, so it's a constant deck width. The skew angle is 30 degrees at all supports. So I wanted to cover 3 different things. One is a starting point of the design, and then we go into Simon's inputs, namely the geometry and loading, and Simon outputs, and then finally some post-processing. This is how we're going to incorporate the report's recommendations by looking at the cross-frame configurations, the limit states, the exterior girder reactions, girder deadload layover, and the cross-frame forces. A little more about the design example. It has a concrete deck of 4,500 PSI, 8-inch deck with half-inch sacrificial cover. The steel girder is going to be 50W, which is the FDOT default grade. Shear connectors throughout the length of the girder. We're going to have the 1% steel in the slab and negative moment regions. And Florida's default for detailed fit is steel deadload fit. The traffic railings weigh 430 pounds per linear foot, no future wear and surfaces or utilities. So one might say, well, where do I start? How do I start setting up the bridges? A lot of states have standards already done for you that you can look at as go-bys. Large corporations have done many types of these structures, so you can take a look at a similar structure. NSBA has produced these continuous span standards, which are fully detailed girders, and they can be supported by the LRFD Simon design program. And also you have all the guidelines from ASTO NSBA Steel Bridge Collaboration, also have the Steel Design Handbook, and even all the other publications, including the old LRFD design examples. So for this design example, we fit in nicely with the continuous span standards, so that's going to be our starting point. But we're going to use the LRFD Simon as our analysis program. And off the bat, we're going to say it's a homogeneous girder, and we're going to set these girders at 12 feet spacing. So one of the first things we need to do to check about the applicability is looking at the geometry, calculate the skew index, we get 0.2. So that tells us that we're in category 2, or theta 30 is less than 50, we're less than the 0.3. And we know that since the skew angle is greater than 20, the cross frames are going to be perpendicular to the girders. A couple other things we need for Simon is the cross frame spacing, so it can calculate the section capacity. So a rough approximation would be span 1 and span 3 will have cross frames spaced at 28 feet, and span 2 will be at 30 feet. You can see I've identified the exterior girders and the first interior girders because those are the ones we're going to look at. I've also identified the dashed lines where the obtuse corners are when we get to flange lateral bending. Some observations: well, we can't use Appendix 6. We got to stay with the code. We're going to use the skew correction factor for shear, and that's also applied to reactions. The cross frames are going to be perpendicular. So if you're going to consider the flange lateral bending stresses, we can compute those based on either the commentary in LRFD or the report's recommendations. And then we also have the modification to the exterior girder reaction. So the continuous span standards have very detailed drawings, as I mentioned. Here's a copy of one. It shows only half the unit. So you have span 1, 140 feet, and half of span 2. The orange boxes are the field splices. The green boxes are potential flange transitions. Now, I have tweaked the plate sizes for this design example so they don't really meet the ones that come with the continuous span standards. So some more information we have to compute for Simon inputs is the dead loads. We need to know the concrete deck weight, stay in place forms if you have them, the haunch weight, and the miscellaneous steel details. Now, Simon internally calculates the steel girder weight, so we don't have to worry about that. And one way to do the miscellaneous steel details is go take a look at the NSBA span to weight curves that they have. And since our maximum span is 180 feet, the square footage of steel is about 30 to 32 pounds per square foot. So we can back out a steel detail factor if we're going to assume 15%, which is a common rule of thumb, that we have about 43 pounds per foot. I also broke out the dead load of the concrete and stay in place forms between tributary area, where you get 1,487 pounds per foot, and equal distribution, where you get 1,331. So you can see by equal distribution, we get about 10% less for our interior girders. And so we're going to assume that the total non-composite load for all the girders is 1,409, and the barriers are all distributed evenly, and there are 172 applied to all girders. So let's look at some of these Simon inputs. I have some screenshots here. I've kind of separated the information between live loads in blue boxes, geometry in green boxes, and dead loads in black boxes. So here you can see the live loads, the distribution factor. We're going to identify it as program defined, so it's going to be calculated internally. The design vehicle is the HL93. We have a dynamic allowance too. We also have geometry of the skew angle of 30 degrees, the girder spacing of 12, and DE, and this is going to be used in computations of the distribution factors. We also have the span length here, and here's the important thing about the cross frame spacing. The span 1 and 3 is 28 feet, span 2 is 30 feet, and span 3 is known as a symmetric span, so you don't have to repeat that information. And dead loads, here's our composite load of 172, and we have the non-composite load of 1,409 per span. And just remember, the Simon programs is not taking into account the flange lateral bending stresses, so we'll have to add that in later. So one thing I'd like to do right off the bat is run the analysis with 0 degree skew and look at the moment and shear distribution factors. And I like to compare it to those default values of 1.02, and I can calculate that the distribution factors based on that is 0.506 and 0.78. And if I compare it to the Simon one, I see that, hey, those default values are really within 10% of using the actual kg. I can also back out a kg factor based on that and then compare it to using the distribution factor of Simon. So here's the distribution factors based on Simon backing out a kg factor, and you can see they change from about 2 to 3 times the amount, yet the distribution factors are within 10%. Using these factors, I can then estimate the skew correction factor for shear, and I get about 9% for span 1, 7% for span 2, and if I use that default value of 0.97, I get about 11%. So I'm going to expect that Simon gives me somewhere between 9 and 11%. So now I go back into the program and put the girder skew angle as 30 degrees, look at my skew distribution factors, compare them to my interior one, and sure enough, I get about a 9% skew correction factor. Here's some cutouts from the program. It's very nice. It gives a maximum performance ratio of the entire girder at 0.92, so I'm less than 1. I'm good. And just looking at span 1 maximum positive moment, looking at fatigue, I'm at about 0.58. And at span 2, pier 2, looking at lateral torsional buckling, I'm about 0.92. And we'll compare that with the exterior girder. So now I'm going to go into the exterior girder. I have to go back into the program, change the girder location to exterior, make some other adjustments. Namely, you got to usually change your effective slab width. And as a reminder, the Simon program does not incorporate the rigid cross-section analysis. So I have 2 tables here, one for moment and one for shear, showing the distribution factors. And each table has 1 lane and 2 lanes. And I have all 3 of them, basically the modification in the interior girder distribution factor, the level rule, and the rigid cross-section analysis. And you can see the 1-lane level rule controls, Simon computes that, but the 2-lane one is controlled by RCA, and Simon does not report that. And same thing for shear, the level rules reported, but not their RCA. But in this case, since my single lanes are about the same or greater, I don't have to rerun the program if I choose not to. So let's look at our maximum performance ratio for the exterior girder now. And you can see it's gone up to about 0.99. Looking at that fatigue case at span 1 maximum positive moment, I'm now about 0.96. And going to span 2, pier 2, you can see that lateral torsional buckling check has gone up to about 0.94. So now we have the girders all working. We have performance categories less than 1. So now we have to start looking at the cross frame configurations, because that's going to determine our flange lateral bending stress and also let us calculate forces for the cross frames. So I've done 2 different arrangements. One's a contiguous cross frame with nuance cross frames eliminated. So you can see with the inner of the spans, they're in a contiguous line. But as I get to the supports, I start eliminating them. And you can see these red, blue circles here. That's where the bolted field splices are, and I have some conflicts here. So, in a final design, you're going to have to make some adjustments. That's the challenge with skewed bridges, missing the flange transitions and missing the bolted field splices. And the cross frame count is 58 here. Here's the discontinuous, or what I call the staggered pattern. And here I get about 57 cross frames. You can see I just staggered the cross frames along the entire girder. Again, I get some conflicts with the bolted field splice here that you're going to have to make adjustments for. And I only dropped 1 cross frame, so I'm sure, like Don mentioned, you could probably optimize this even more and drop some more cross frames out. But I want to talk about the comparison of the flange lateral bending stresses with the two different cross-frame configurations. Here is bridge 17, which has a contiguous cross-frames. And what we're looking at in this graph is the strength 1 bottom flange lateral bending stress. This is the stress along the y-axis and the girder length along the x-axis. And you can see at the point of support or near the support, we have about 11 KSI, and then it kind of goes very small along the girder. And then the central girder does have a peak at the supports, but nothing as great as the exterior girders. For the staggered pattern, I showed two different types, one with an OBF ratio less than 4 and one at 4. And you can see for bridge 8 here that the bottom flange lateral bending stress is peaking at every staggered point, but very small. But at girder 3, which is close to the central girder, you can see the peaks go quite high, up to about 24 KSI when we're within the span. Now with the offset better than 4, that drops down to 13 for bridge 4. So when we look at this chart, just to show you where some of these numbers might come from, you can remember that bridge 17, we were about 11 KSI for strength 1. We divide that by the load factor, we get about 7, and the chart shows 8. And for the two stagger patterns here, we have 24 divided by 1.6, which is 15, which is shown in the table. And the 13 divided by 1.6 is 8, which is compared to the 10 KSI shown in the table. So for this design example, I'm choosing the contiguous cross-frame pattern, and I have to figure out now what my offset to BF ratios are so I can determine my flange lateral bending stress. In this table, I have the girder, the exterior, and the first girder, and at each location, end-bent 1, pier 2, which is the back or the head of it. And so, for example, here at end-bent 1, at the exterior girder, my offset's about 14 feet, so 14 feet times 12 divided by the 16-inch flat flange, I'm about 11. Other locations, I get back down to 9, but you can see I'm clearly greater than 4, so this is the column I can use. Showing that how it lays in with the girder framing plan, you can see at the exterior girders, all the obtuse corners, I have the 4 KSI, and at the interior girders, where I have discontinuous frames, I have the 5 KSI labeled. So we have to remember that those are unfactored stresses, and as Don mentioned, as we check the limit states, we have to factor those up accordingly with this weighted average load factor. So how do we do that? Well, let's take a look at limit state strength 1, which we're mainly going to be controlled by 610.7 or 610.8 in the code. And you can see both of them approach flange lateral bending the same with dividing it by 3. In our case, we're going to check the exterior girder section at 90% in span 1, basically at 126 feet, the flange transition. And we're basically going to be controlled by the 610.8 composite sections and negative flexure. Simon gives us a nice summary of all the flange stresses. We see the performance ratio, and now we can calculate the flange lateral bending by multiplying it by the load factor. So for example, the exterior girder is 4 times 1.6, 6.4 KSI for strength 1. So now how do we recompute our performance ratio? Well, we know from the Simon output, our bottom flange stress is 37.2 KSI. Our flange lateral bending for the exterior is 6.4, but I'm going to just use the 8 KSI from the interior so I don't have to do both girders and be a little conservative here. So here I'm going to use the 1/3 rule, adding the 37 plus the 8 divided by 3. So my new revised factor tip stress is 39.9. I can back calculate FNC out because I know the performance ratio. So the FNC is 40.9, And now I can recalculate the performance ratio by dividing those numbers and getting 0.974, and I'm still under 1, so I am good. Service 2 is very similar, and we can check the bottom flange by just dividing the lateral flange lateral bending by 2. Again, we're looking at the exterior girder span 1 at 90%, and the assignment gives us our service 2 bottom flange stress of 25. So I have our 25 KSI here. My flange lateral bending is 6 KSI. That comes from factoring up my 4 and 5 KSI by 1.2. And you can see, again, I'm going to be conservative and just use the interior girder as a 1 check for both of them. So the 25.68 plus half of the flange lateral bending stress, my new revised factor stress is now 28 KSI. I divide that by 0.95 XY, and my new performance ratio is 0.604. So now we're going to get to fatigue. And one of the first things you might want to notice in fatigue is how it states that for horizontally curved girders, the fatigue stress range should be the addition of the major axis bending plus the lateral bending. And they don't really mention anything about skewed bridges, but this is how I've applied flange lateral bending to straight skewed steel girder bridges. Now, we've been checking the exterior girder span 1 at 90%, but when we look at the stresses, the bottom flange is consistently in compression, so there's no fatigue concern there. And it even shows that they don't check it, it just checks the top flange. I now go over to span 2, where my other 2 points are, about 14, 15, 16 feet away. And you can see that, again, the bottom flange is in compression, so I don't have to worry about fatigue because I don't get into tension. So now I'm going to move over to span 1 at the obtuse corner, and you can now see at this location, the bottom flange is in tension, so I'm going to have to incorporate the flange lateral bending stress. So two big assumptions here. First of all, the code, the flange lateral bending stresses is in the commentary, and I'm going to be also assuming that I'm in fatigue 1. So Simon gives me all the nice stresses that I pointed out before. My stress range in the bottom flange is 6.3. Now that's really at the bottom of the bottom flange, so I can actually ratio the neutral axis from the bottom flange to the top of the bottom flange and kind of decrease that a little bit to 6.2. My flange lateral bending is 7 KSI. That comes from the 4 times the load factor of 1.75. And then I just directly add those together and divide by 12. The 12, remember, this is a connection detail. I'm under fatigue 1, which is the constant amplitude fatigue threshold I'm now checking, which is 12. And you see I'm not good, I'm at 1.1. So you have a couple options here. Option 1, you increase the flange area and get the stress under 1. Another option might want to be using a bolted tab plate. Remember, we're looking at flange lateral bending. So at the tip, it's not 0, but at the center, it is 0. And Simon actually reports that near the bottom of the weld near the bottom flange is working fine. So, you might want to contact the owner of the state and some fabricators and see what they think about using the bolted tab plate, because we only have to use this in 4 locations. You don't have to use it in any other locations except these 4 locations. So let's move on to service 1, optional live load deflection. Here, Simon computes it based on equal distribution, which is the 4 lanes times the multiple presence factor divided by 5 girders. So simply, I just have to ratio the controlling moment distribution factor by those equal distribution factor and multiply it by the deflection Simon calculates. So 0.544 times that ratio I get 1. I'm still under L over 800. I can do the same thing for span 2, which deflection is 0.801 times that ratio. I'm at 1.4. I'm still under L over 800. So while it's a significant increase, I'm still okay meeting the code, the optional code, that is. So here's an example of computing the exterior girder reaction. I'm going to look at the obtuse corner here of NBENT 1 for exterior girder. Simon gives me all the dead load reactions. I can sum that up to equal to 90.5. It also gives me the maximum vehicle reaction of 126. And we have to remember that Simon, since it was controlled by the level rule here, I already have the skewed correction factor incorporated. So you don't want to double dip here. So I'm going to use my strength 1 equation, factor the dead loads and live loads up and get 334, and then take the report's recommendation and bump it up another 10% and get 368. If you want to calculate the girder dead load layover, Don went over that method. Basically, you're looking at the 10th point, the deflection divided by that length, the arctangent of that, and that's your angle of rotation. You can then calculate the angle of twist or out of plane rotation by multiplying that angle by the tangent of the skew angle, and then the layover is simply the tangent of that angle times the depth of the girder. So putting some numbers to it, we can go to Simon and look at the non-composite dead loads, which is my concrete depth weight. And remember, since Florida default value is a steel dead load fit, my webs are plumb at steel weight only. So I want to calculate my angle of twist by looking at the 10th point deflection, dividing by that length of 14 feet times 12, and my angle is 0.25 degrees. My angle of rotation, out of plane rotation, that is, you just multiply that angle by the tangent of the skew angle, which is 30 degrees, and I get a phi of 0.15. I then can multiply that by the web or girder depth, and I get a layover of 0.2 inches. So now we're going to get into the last part of this, and that is the cross-frame forces. And I just want to make a couple of comments about this. When I graduated and started my professional career, we did a lot of line girder analysis for skewed straight girder bridges. And basically the company policies were you design for the minimum KL over R, you look at wind, and don't use an angle smaller than this size. And that's how we did lots of bridges. Later on, we started looking at stability forces. There was recommendations between 2 to 6% of flange forces. So we started using that. And then as the code got into more constructability, we started looking at the forces to the overhand bracket loads. AASHTO LRFD also started adding information about recommended values for checking for fatigue of the 20 tip force. And then, of course, people started using refined analysis, and you got your forces derived directly. And I'm sure there's other ways people have used to calculate cross-frame loads. And there's always a question is, do we also design these for fatigue? Because on a line girder analysis, we never even had that information. Don showed you this chart. Here we are in this cross-frame case 2I because we're a contiguous intermediate cross frames. And I'm going to calculate the forces for strength 1. So we're at these coefficients here. So again, let's look at first some reminder of the definitions here. Basically, you're going to take the maximum shear and times it by that coefficient, and then we can calculate the top and horizontal components using those coefficients and the ratio of the maximum moment divided by the distance between your chords, which you have to determine either for your non-composite loads or your composite loads. So now let's look at some numbers here. Shear is right here I have both exterior girder and interior girder, and both basically the moments are similar and the shears are similar, so I'm going to just use the maximum of the both. Shear's quite straightforward. My ratio coefficient's 0.09. My maximum shear is 535, so I get 48 kips for my panel shear. To do my horizontal forces, I got to need this depth, this dimension between the mid-depth of the slab and the mid-depth of the bottom chord, because remember, I'm looking at strength 1, so I can use the composite section here. So I have some assumptions here to calculate that. My web is 7 to 8 inches. I have offsets, and I have my haunch of 4 inches and my mid-depth of the slab. So I get 80 inches. So that's my HCFC. So I take my maximum moment times 12 divided by that value of 80 inches times that coefficient, and I get 168 kips. In this instance, the top chord is half of the bottom chord. So basically, I just have to take half that amount, and I get 84 kips. So now I have my panel shear 48 kips, my top horizontal force of 84 kips, bottom chord is 168. I'm using a K-frame here with the diagonal going up to the top chord, so I know my bottom chord is 168 kips. So I need to calculate the angle of the diagonal to calculate the force in the diagonal, and knowing, again, with some assumptions, recalculating HCF for the non-composite, I calculate that angle as 43 degrees. I know the diagonal has to take the entire vertical load, so 48 divided by the sine of 43, I have 71 kips. Now, since I don't know which way these forces are going, I'm going to have to assume the worst and add the horizontal component of the diagonal force to the 84 kips and get my top chord force of 136. So you might take a step back and go, wow, these are a lot larger than I usually design for, or this is what I'm accustomed to. So I just want to go over some of the assumptions in these coefficients. So let's look in the report. Figure 1, figure 100 is shown here. This is the strength 1 bottom chord connection, horizontal force. And you can see the case 1I is the black diamond, and our case is 2I is the blue dot. And you can see for case 1, they're all under 0.03, and that's what's in the table. But case 2I, there's a lot of variations of that coefficient from 0.025 all the way up to 0.075, and the limit was set at 0.08. So that's what's in the table. And similar is the strength 1 shear force ratios. You can see that case 2I can vary from 0.025 to almost 0.09, and then in the table is the 0.09. So we got to keep that in mind when you're using these tables. If they start getting unrealistic, you might want to do a refined analysis. I just want to thank you for your attention, and FDOT always has a safety message. This one is, please don't text and drive, and Don will do the wrap-up.
Okay. Thanks, Dennis. So just a quick few comments to conclude. We hope that you've gotten a good impression here that line girder analysis can be employed to obtain a fast, efficient, and effective design solution for a fairly wide range of straight, skewed I-Girder bridges. There's definitely a limit to this, and so at some point we moved to where we would need to be considering a refined analysis. And I think the projects contributed a little more to the state of knowledge here in terms of when that needs to happen. We hope that this can be useful to you in your design and your rating of these types of structures. And that's about it. If I can get it to push. Yep. Thank you very much for your attendance. and we'll be glad to handle questions and wrap up from here. So, Nate?
All right. Thank you, Don and Dennis. So we're a bit over time, but do want to get to a couple of questions here. And as we usually do for our audience, we do pose one poll question to the audience. So let's start with that and then get to one or two questions here before we part. And the first poll question you should see in your moderator window. True or false, the three-dimensional aspects of the bridge response and the sufficiency of I-Girder analysis for design can be related closely to the bridge skew index and the bearing line skew angles. Is that true or false? You can select the answer you think is right on your computer screens there. Is that a true or false statement? So let's go ahead and go to the results. And Don, it looks like overwhelmingly the audience thinks that that is true. Did they get that right?
Yeah, I guess we've got a really smart audience and someone that doesn't agree with us.
Always a contrarian or two out there. All right, let's go to slide 38 for a question. And let's see here. The question is, do we think that the concern for live load deflection predictions, the recommendation to use the moment distribution factor rather than the NL over NG convention, is that truly a skew phenomenon, or might we find similar concern with bridges that are more or less unskewed? And I'll put that to you, Don.
Okay, yeah, I guess I think if you have a bridge that's a tangent bridge with skew angle of 0, and you've got basically equal girders across, then this is a reasonably good assumption. It's essentially based on equal distribution of live load to all the girders. So I think that's a fairly reasonable assumption there. But what we're seeing is that once you have a bridge with skew on it, you can definitely get some effects of the torsional action of the bridge that give you some live load deflection results that are going to deviate from that a bit, that idealized assumption a bit.
All right, let's do one question for you, Dennis. I'm going to go to slide 51. The question is, for the exterior girder live load distribution factors, the approximate equations are independent of span length. Why does span length not come into play for the exterior girder live load distribution factors?
Yeah, maybe Don can help me with that, because that all those equations are all based on the NCHRP report that determined the moment distribution equations and the shear equations. And I don't remember, they probably did a regression analysis on the results and determined that length was not a significant variable for shear. But
anything to add, Don?
Yeah, I think that's a good answer. That's a very good question. Honestly, I would have to go back and dig up that report and look back at it again to really be able to answer it well, I think.
All right. Well, we are over time. Unfortunately, we won't be able to get to any more questions.